Hello friends, today I'm back again trying to demonstrate an example of MIPS architecture and how an overflow sort of works for MIPS architecture. In this case, I'm going to show a small part of the MIPS assembly code that I have written for one of the demo exploits. My goal in this case is to sort of give small examples with respect to the MIPS architecture and basically explain how buffer overflow can be exploited in MIPS. In this case, basically, I'm going to show you the static disassembly of a specific binary, and then in the second part, I'll actually show you how to overflow it as a normal buffer overflow. So, in this case, if we look at the specific program right now, you can observe that this is the main function, and I'm using IDA Pro for disassembling this specific assembly. It's much more easier to use IDA Pro for this aspect than anything else. In this case, what we can observe is that this is the main function, and there's a call to string copy over here. Normally, when I see string copy functions, I know that there's a good possibility that if user input is taken in them, they are going to be susceptible to buffer overflows. This is a classic example of a standard buffer overflow. The only thing that differentiates this from other architectures is with respect to how the functions do take their arguments. In MIPS, basically, there are three important aspects. One thing is MIPS, in this case, is little endian, so obviously that aspect goes with all the architectures. But one important aspect is the fact that the registers are primarily used for providing arguments to different functions. So standard registers that are used are A0, A1, A2, and A3. Every other argument after that is laid out on the stack. MIPS also has scratch registers from S0 to S7. Those are 8 scratch registers. They are basically used during the whole time a program is getting executed inside a function. They usually store the values that are temporary values usually, and they are very handy and useful when you do a buffer overflow exploit because they help you to sort of adjust and align the stack. The other aspect that comes into picture also is the T9 register. This one is a special register. It seems like T9 is primarily used in MIPS architecture for loading function addresses most of the times. So if you're looking for raw exploits, it's a good aspect to look for T9 and any scratch register being loaded into the T9, because that can help you to do a return to libc sort of function exploit very easily. However, getting back to our simple buffer overflow, what we are going to do is basically read through the assembly instructions and identify how this buffer overflow can be exploited. So if you look over here, the first instruction is add IU $SP-288. So it seems like this is a prologue, and usually the prologue includes, moving the stack pointer certain number of bytes depending on how much is allocated by the compiler, and also basically storing the return address on the stack. MIPS is sort of similar to ARM, in which there is a return address register which actually stores the return address when a function call is made. So when the main function is actually called, the actual return value is actually stored in $RA, which we can see over here. However, when the prologue is being executed, the value from the register is always put into a stack pointer. And so that becomes useful for us because now we can override the value and control as usual in a regular buffer overflow, especially in a stack buffer overflow, the exploit. So in this case, what we are going to do is basically read through the assembly. So we can see that add IU SP-288. So it's basically moving the stack pointer 288 bytes downwards. In this case, the stack grows downwards from an upper memory address to a lower memory address. And so it's storing the return address at the stack pointer plus 284. And so basically the value is being stored on the return address. Then it's loading the global pointer with an address. And usually in MIPS architecture, the global pointer is used for pointing towards the base address for loading the functions from libraries such as libc. Those are the ones that are pointed towards the aspect of that. So the value is loaded with $GP. This specific value is loaded, which is sort of the return address for the libc based system modules. Then also, after loading and adding the address, it basically stores that CP value into 16 bytes below the stack pointer. What we can see over here is that if you look at it, IDAPRO is pretty good. It has already pointed that this is the destination. And so since string copy takes two functions, string copy's argument is string copy, destination, and source. So A0 will contain the destination, and A1 will contain the actual source. If you look at it, it seems like A0 is being filled up with at a specific pointer value. So this is, if you look at the actual address, it's 24 bytes down the stack address. So basically, at the address of stack pointer plus 24 is what gonna be the destination address. So basically, we can clearly see that the destination is on the stack, which is a good part for us because now we can easily exploit the stack overflow. The load word loads basically some value from, so it seems like this is an array and it loads the second value from A1 since it's adding 4 bytes to it. And so basically in this case, this program takes basically arguments, and arg0 is obviously the name of the function, the name of the program, but arg1 is basically the first argument that you pass. And so it seems like our argument that's passed is loaded into $A1. We had already talked that the first four values for a function are always taken from A0, A1, and A2, A3. So in this case, we can see that A1 is being loaded with this specific address. It loads, as I had said, $T9 with string copy address. There's an op instruction. And finally, it does a JLR. A JLR is basically jump to the address and link it to a return pointer. So basically at that point, again, it's going to jump and link the return pointer. The return pointer obviously is going to be loaded with the new value, which is going to be this value. But this is for this specific string copy. What we are interested in is when the actual JRA is done in the main function. When we do a string copy, as we had observed, since the destination is 24 bytes, about stack pointer, we'll have to basically overflow it with 284 minus 24. That's 200 bytes, and 244 bytes. Actually to 60 bytes, my apologies. But basically we are doing, so we have to add 260 bytes to our string, which is going to be the argument, and then override the 4 bytes of the return pointer at that point of time. So basically, once we have a string which is made up of, let's say, 260 A's, you will be overwriting the return address with the last 4 A's that are being copied into it. Finally, after that, it loads again the old value. It does a load $A0 hello %s. Printf obviously takes two things. One is the actual string that's supposed to be printed with %s, which is indicating a string, and then the actual destination. So we can see that $A1 is again loaded from the specific, which is the destination address. So it's basically calling printf and printing that specific function value. So it's going to say hello with whatever you're going to print out. And basically JLR $T9 does the actual jump to the printf, completes the printf, and returns back. When it comes back, as we had seen in the earlier case, it loads the stack pointer with $GP values. Now obviously this is also going to be sort of spoiled because of the fact, well actually not, because it's only 16 bytes and we are covering up to 24 bytes. So basically the GP gets loaded up with 16 bytes down with adding SP. Finally $V0 is moved with 0. V0 again is a pointer, as in you would know that EAX is in x86. V0 is the return value for any function. So in this case, when string copy comes back, it basically lets you know what the V0 would be for that specific function. Similarly for printf, whatever would be the return value is going to be loaded up with $V0. Finally, the main point is loading $RA. So in this case, we can see that from 284 bytes plus SP, the value is being loaded to RA, and that's going to be our value. And so when it does a JRR, that's where we will be able to control the stack and jump to our specific exploit. So in this case, in the next section, I'll show you how basically the exploit works, and we will jump to a function that basically wasn't being called anywhere in the actual program, but we are able to jump to it by doing a stack overflow. So that's pretty much it from me for today. This is a small introduction to MIPS, sort of buffer overflow, and how to read the disassembly for a MIPS Little Indian architecture. Thanks again.